Okay, good morning. Let me start the class. So we have completed seeing the machine part. Conversion of NFA to DFA, then DFA to a regular expression, whatever. So today, what we are going to see is we are going to check the language little bit deeper. Okay. And then I have already told that the language which is accepted by finite automata, the language which is accepted by finite automata is known as regular language. Regular language. Now, today we'll be dealing with this regular language alone. So now, when I let's forget about this regular for the time being. When I talk about language, right? Let's consider this normal English spoken language. Okay. So in our normal spoken English language, right? What we used to study, if you want to be very strong in English spoken or writing skill, means we have to understand the grammar. Language. No. Noam Chomsky. In 1956, right, he's a mathematician. He developed a mathematical definition of a grammar. Mathematical definition of a grammar. I have already told grammar is the backbone of the languages. Languages we can consider like a collection of sentences. So grammar is the backbone of sentences. So once we understand this grammar, right, we can easily generate a language. Now, see here, why mathematical definition? Everything, the blueprint of every concept which we will like to implement, right? If we have the mathematical definition of the or the mathematical model, it will be easy for us to implement. That's why every scenario, every problem, right? We just want to design a mathematical model of that particular problem to be solved in an easier way. So this Noam Chomsky, right, in 1956, he developed a mathematical definition of a grammar, which will be represented by G is equal to N T P S. N is nothing but finite set of non-terminals, mostly represented by capital letters. And then this is the finite set of terminals equivalent to input symbols. And then this one, right, let me call this as production. Let me call this as production or set of rules. And then this indicates the start symbol. And then I've already told at the beginning of this paper, we are going to study 4 types of machine, correspondingly 4 types of language, correspondingly 4 types of grammar. So now this NTPS, right? I'll be defining this specifically in terms of regular grammar. The grammar which could generate regular language is known as Regular grammar. Regular grammar. Okay. So this NTPS term, right, I'll be defining specifically with respect to this regular grammar. And then I've also mentioned that for all the four languages, we are going to watch out for four different types of grammars. So this grammars, right, mainly based on this production or set of rules, they have been classified. So now let me take one example. Let me take one example. Yes, it's silent. Undefined letter. So let me just uh, let me just and then in the finite automata we have seen initial state, right? So every grammar needs to have a start symbol. That start symbol is represented by S. So in my case, S is same. I mean S is going to be the start symbol. So I've considered S is equal to S. Sometimes you may find different non-terminal or a capital letter. So it's up to you. But in order to avoid many errors, right, please use S as the default start symbol. It's not fixed, but in order to avoid certain errors, right, please do use S as the start symbol. Or it could be written as or. Now, now let me explain those terms. M is the set of non-terminals. I've already this one capital alphabet. Else in the case of equivalent to input symbols. And then S is the start. Production rules are of this form. Production rules, let me explain something about this production rule. Production rules, right? Let me say alpha this one. What do we mean by production rules is wherever you find this alpha, right, it can be replaceable by beta, or else you can say that instead of saying replaceable by beta, you can say that alpha can derive this beta. Okay, certain terms are there. So either you can say that alpha can be replaceable by beta, or else you can say that from alpha you can derive beta. Okay, now these are the production rules. Production rules always consist of left hand side, left hand context, and then right hand side. So most of the time we'll be finding non-terminals on the left hand side. Okay. Now let me number this one. Let me number this. Let me use this production rules for. I'm considering you guys as a beginners, so let me use this one. I've already told instead of this, you can convert. You can write like this also. For the time being, I'm considering you guys as a beginner, so let me use this production rule. Now let me try to derive certain strings using this production rule. So likewise, in the case of finite automata, everything has to start from initial state. Likewise, in the case of grammar, you have to start from the start symbol. Now let me start, if you're going to derive something, you have to use this symbol, derivation symbol, AS. So let me inform that I'm using the production rule number 1. Okay, in exam you need not underline this non-terminal, but right now I've already told I'm considering you guys as the beginners, so I'm doing it in that manner. So now whenever you find this non-terminals, right, they can be derivable to certain terminals, or they can be replaced by certain terminals or non-terminals. Now again, this S can be replaceable by either B followed by capital A or A followed by capital S. It's up to you. There is no restriction. So I'll be using another one, A. I'm using operation rule number 2. Now again, A. A got two options. Either you can replace A by C followed by capital A or epsilon. So let me use number 3, A, B. Instead of A, I'm going to replace by C, A. C, A, this is 3. And then A, B, C, epsilon, this is 4. So instead of A, B, C, epsilon, you can write simply as A, B, C. So using this particular production rules or from the given example, given regular grammar, right, I can generate a string of ABC. Now, this is not the only string possible which can be derived using this particular grammar. So let me try for another string. Let me start for AS. This is 1. And then instead of A, then BA. Okay. This is 2. Then A, B, epsilon. This is 4. AB. This is another string which could be derived using this one. Now let me try for another one. S, I have already told either S can be replaceable by A followed by capital S or B followed by capital A. But whenever you want to derive something, you should start always from the start symbol. So let me go for this BA. This is production rule number 2. And then B, instead of A, I'll be selecting A, C, A. This is production rule number 3. B, C, then epsilon, this is 4. This is B, C. This is another string. This is string number 1, 2, 3. If possible, whether any possibility is there for different one, yes. Let me try. B, A, this is 2. Then instead of A, let me go for epsilon, so 4, so I can derive B. Next, any other possibility? AS, this is using 1. And then this is ABA, this is using 2. And then, oh, AB, I guess it's completed already. ABC completed, AB completed, BC completed, B completed. This is already completed. Epsilon is completed. B completed. Then what about BA? BA. Okay, B completed. So I guess no more. So using what are the languages which could be generated with this? Okay, let me take another example. Let me take another example. SAS, this is using 1. A, again, there is no restriction that once you have used one production rules, you cannot repeat like it. There is no restriction. So I'll be using that one again. This is 1. And then AA, then BA, this is using 2. AAB, epsilon, this is 4. Implies that AAB. Got it? So what kind of language could be generated? Let me go for another string. S, B, A, production rule number 2, and then B, C, A, production rule number 3, B, C, C, A, again production rule number 3. Then BCC epsilon 4 implies that BCC. So what are the strings we could generate? Means either we could generate A, B, C, then C, 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 like that we can generate. Then what else? A, B, C, C, C we can derive. Then B, C, 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 C we can derive. Then what else? A, B, we can derive. Then what else? Single B we can derive. Then B, C, C, oh, it's already there. So these are the possible language. These are the possible language which could be derived using this possible string which could be derived using this particular grammar. And then one more thing, in my class, right, I have tried to generate possible string of first, second, third, fourth, fifth, sixth. So many possibilities might be there. You please go back and check it by yourself. This is one example of regular grammar. So how to define the grammatical definition of this particular grammar means you have to write G is equal to N comma T comma P comma S, where P is this, N is this, T is this, then S is equal to S. This is one example. Now again, another topic within this regular grammar. Regular grammar are either right linear or left linear. Now before I explain this, right, let me again go back to this example. Before I explain this, let me go back to this example. Now this particular example, right, where I am, okay. This particular example, for this particular scenario, let me consider this one. Okay. Now, okay, fine. Let me, you will get confused. Let me just rough it. I'm going to consider you guys as a beginner, so I'll just rough it. I have already mentioned that depending on the production rules, the grammar will be classified into 4 types. Now, we are going to generalize this production. Now, as per the definition of the production, I've already told that they'll be of this format, alpha replaceable by beta. Alpha is nothing but N union non-terminal union terminal. This is also N terminal and N union terminal, but epsilon could be included. But on the left-hand side, you can't. Okay, this is the scenario. Or replaceable by beta, that's it for the time being. Complexify the thing. Now, let me generalize this production 1. On the left-hand side of this arrow, F non-terminal. So let's write non-terminal, which can be replaceable by terminal. A is nothing but terminal. So T I'm writing followed by non-terminal. What about number 2? Yes, number 2, non-terminal replaceable by terminal followed by non-terminal. What about number 3? Non-terminal replaceable by terminal followed by non-terminal. Number 4, non-terminal replaceable by epsilon. Okay. Now in this particular generalization procedure, right, I'm going to add 1 point in the definition of regular grammar. A grammar will be considered as regular grammar when the production is of N epsilon and terminal N or N epsilon terminal N. Okay. A grammar will be defined as regular grammar if the production of the grammar follows this format. If you want to identify a given grammar as regular or not, then you need to check the production of the given grammar, whether the production is following this format or not. This format means first case is N can be replaceable by epsilon, or else N can be replaceable by single terminal, or else N can be replaceable by single terminal followed by single non-terminal, or N replaceable by epsilon, N replaceable by terminal, N replaceable by single non-terminal followed by single terminal. If the production is of this format, then you can conclude that the grammar is a regular grammar. Now let me check for this. This example I have purposely considered, I have purposely selected a regular grammar. So definitely this is going to be a regular grammar. So let me check whether this is being followed this particular time. This is left hand side consists of single non-terminal in all the production. Yes. What about the right hand side of all the production? This is epsilon, whether it's included in the type, included in the definition. Yes. This is single terminal. This is single non-terminal. Yes, one of the kind. This is single terminal followed by single non-terminal. Single terminal followed by single non-terminal. Okay. Hence, this is the regular grammar. Now again, now let me move down. I've already told that regular grammar are either right linear or left linear. Right linear or left linear. Now let me define one more thing. Okay. Now in this case, there are two types. Both are having a common type, and this two, I'm dividing this two by this OR section. So epsilon are common, terminal common. In this case, the position where the non-terminals or terminals are placed, it's quite different here. So based on this, right, we are going to term this regular grammar either left linear or right linear. Now, when the non-terminal is towards the right-hand side, not right-hand side, towards the right side of the terminal, then such kind is known as right linear. Right linear. And then when the non-terminal is towards the left side of this terminal, then such kind is known as left linear. Okay, that is the definition of being right linear or left linear. Now let me take another example. S replaceable by AA, then S, okay, AB, and then A epsilon. Then S replaceable by AA, S replaceable by BA, A replaceable by epsilon. Now see here, I have considered two examples. I'm going to linear or left linear. Let me take another third. Okay. Now how to check that one means let me write let me use different color. This is N, this is T, this is N. This is N, this is T, this is N, this is T. This is N, this is epsilon. This is N, this is terminal, this is non-terminal. This is non-terminal, this is terminal, this is non-terminal. This is non-terminal, this is epsilon. And then for this one, this is non-terminal, this is non-terminal, this is terminal. Non-terminal, non-terminal, terminal, non-terminal, epsilon. Now, as per the definition we have just seen in the case of right linear and left linear, right? Right linear means non-terminal this. Left linear means and non-terminal this. Now in this example, right, I'm seeing mixture of these two. Right linear as well as left linear. See here, terminal followed by non-terminal is right linear, non-terminal followed by terminal is left linear. If it is, whether it's a regular grammar, even though you might be thinking that it's a regular grammar, you cannot mix both right linear and left linear in one example or in one, in one question or one example of generating a string or language. So this is not the right way for writing a regular grammar. What about this? This is completely right linear. What about this? This is completely left linear. So if you want to construct a regular grammar, you have to construct completely a right linear or else a left linear. You cannot mix both while constructing a regular grammar. This is a few tips. And then I won't be taking any other example. You do one thing, you please practice by yourself. And I'll be starting the exam right now. So just wait for a while. Wait for a while. Atul Sharma, unmute your mic and respond to your call. Atul Sharma, absent. AR Sorintri,
Present.
absent.
Present.
Okay. Dayasagar Kumbhatabam, absent. Then Chaitanya Agrawal,
Yes, ma'am.
Jagdeep Singh,
Yes, ma'am.
then Manjeet. Oh, Manjeet is facing some internal issue. Okay, then Lufo. Lufo, absent. Saket Kumar Ray. Saket Kumar Ray, absent. Srishti Katiyar, absent. Siddharth Sinam, absent. Warepam Mangalsana,
Yes, ma'am.
okay, fine. You do one thing. Kari Lasmi Narayana,
Yes, ma'am.
okay. Vishwasena Vishnu Simha,
Yes, ma'am.
okay. So you do one thing. Everyone just log out, and then not everyone. Wait. Let me stop sharing the. Let me select. Enrollment number 1, enrollment number 4, enrollment and enrollment number 14, enrollment number 18, enrollment number 21, enrollment number 28, enrollment number 33, enrollment number 45, enrollment number 51, then enrollment number 55. You guys stays, others please log out. No, or else I'll do one thing. For enrollment number 1, 4, 7, 9, 14, 18, 21 and all, please log, everyone just please log out. I'll send a different Gmeet link. Okay, let me end this session and then